Today we're going to look at a little different way to explain the derivative of an exponential. And I've already made a mistake here, and I can't erase that. I don't know why. This should be n to the x. So if we have a function, say 2 to the x or 10 to the x, then, well, our material showed going through the definition of the derivative, that f of x plus delta x minus f of x all over delta x. So we take the limit as delta x approaches 0. This exponential derivative would turn out to be this. And then intuitively, we were shown what this turned out to be. Well, I've had a lot of students say, well, why did that come up to be it turned out to be the natural log of n? Okay, so we're going to look at this a little bit differently. Our material showed that the derivative of n to the x was simply n to the x times the natural log of n. And this is where that natural log of n came from, although mathematically we didn't see where that came from. It was more a numerical, see what this is leading us to. Well, today we're going to look at a little more concrete way of showing this. But in order to do that, we needed the implicit differentiation idea. Okay. Now, let's before we get into the exponential, we need to use a certain fact, and that is our logarithmic derivative. If y equals the natural log of x, then y primed or dy by dx will be 1 over x. Because of the relationship between exponential functions and log functions, we have to be able to use one of the derivatives in order to find the other. And to be able to use this one, we would have to define natural log of x in a little different way, a little more advanced, and we're not quite there yet. By the end of the semester, we'll be able to do that, but we have to take that for granted and say, okay, this is true, this is a fact, and from this fact, we'll be able to show the other formulas that we developed on the way up to today. Now, before we look at the exponential function, 2 to the x or even e to the x, let's look at the log function of a different base. Now, in this one, natural log of x, we're using log base e, which turns out to be very nice to work with in calculus. As we see here, the logarithm doesn't even show up as part of the answer to the derivative. It just turns into 1 over x. But as we looked at logs of different bases, we see a logarithm, a natural log value show up. And I had a few students ask, well, how did we get that in the formula? Well, hopefully today this will kind of clear up some of the how did we get that in the formula questions, a few of these questions. Let's look at log of x base 3. Okay. By the formula that was talked about in our material, the derivative of this would turn out to be 1 over the natural log of 3 times x. Natural log of 3 times x in the denominator part. Well, today we're going to start out by showing how we end up with the natural log of 3 in here, and then we'll be able to go on to the exponential function and show where the natural log shows up in that as well. Well, the log of x base 3, we've got to do some algebra first before we can figure out where this comes from. Through the relationship of logarithms and exponential functions, algebraically we need to change this to the exponential equivalent. Okay, and this would be written as what in exponential form? Okay, we take 3 to the y equals x. Well, I find students think of it easier, this loop-de-loop thing I do with the logarithm. So the base of the logarithm is also the base of the exponent, and then this turns out to be the exponent, and 3 to the y then is going to equal the x. By definition of inverse functions, logarithms, and exponential, one means the other. If we have one form, we can automatically change it to the other form. So really, this arrow will actually go both directions. It's like an equal sign. If we know one, automatically we know the other. Doesn't matter which side we start with. Well, here we're starting with the logarithm, but we're going to be using this equation. And we're going to take the natural log of both sides, again using some algebra properties here. This equation, whatever we do to one side, we do the same thing to the other. The logs, taking the logs of both sides, is a valid equation property. So we can do that. And then, with our log properties, what can we do with the y? Okay, bring that out front. So y times natural log of 3 is going to equal natural log of x, which then, solving for y, natural log of 3 is a number. Now, natural log of 3 is about 1.1, 1.09 something or other. Okay, so it's a constant, and to solve for y, we divide by the coefficient, divide by natural log of 3. So y turns out to equal natural log of x divided by the natural log of 3. Now, this is a long way around what some of you may have seen in algebra, the change of base formula for logarithms. This is why we can say we can change the base of any logarithm. If we have the log of, say, x base a, we can change to the log of x to some other base b divided by the log of a with that same base b. So in this case, we're using e as our base, as what base b would equal. So we're taking, back to the very beginning, the log of x base 3, we can change that to the natural log of x divided by the natural log of 3. So algebraically, we're changing our original function into this form. Now let's see what we can do with the derivative of that. So we have our log of x base 3, which we've changed to the natural log of x divided by the natural log of 3. Or, to get a better grasp on what this value is, we can rewrite it to 1 over the natural log of 3, which is a constant, just like 1/3 or 1/2, 1/10, okay? And then times the variable part, natural log of x, okay? So, we take the derivative of y with respect to x, which again originally is this. We want to look at it in this form. We would have the constant times, well, what's the derivative of natural log of x? 1 over x. So this is where the natural log of 3 shows up in the derivative of log base 3. And normally we write this just as one single fraction, but it makes a little more sense when we separate it into the two parts. Okay? So questions why the derivative of logs, different bases, turn out to be this? Any questions about that part?
So then it's not like the normal formula that we were given?
This is the formula you were given. It was devised in a little different way. But yeah, this is, what did our material say? Log base A, log of x base A. Derivative of any logarithm to some base A is going to be 1 over the natural log of A times x in the denominator. Okay? Now we'll take a look at this question, getting to the exponential. And again, as we looked at this material, this was the first thing introduced, and then the logarithms were introduced after that. So this is kind of switching it around, and it might make a little more sense for some of you. But based on the idea of the logarithms and the log properties, let's start out with y equaling 2 to the x. Okay, that'll be our function. Then, as we did with the log explanation, let's take the natural log of both sides. Okay, so the natural log of y would equal the natural log of 2 to the x. Now, because of the log properties, what can we do with that x? Okay, pull it out in front. So we'd have the natural log of y equals x times the natural log of 2. Now, natural log of 2, again, is a constant, a value. In this case, it's about 0.693, something like that. So that's just a coefficient of the x. Now, we're trying to find the derivative of 2 to the x, or in notation that we've used, we're trying to find dy by dx, or y primed. So let's go ahead and take the derivative now of both sides. Well, this side is a little bit easier to deal with. Derivative of x times natural log of 2 would turn out to be what? No. Natural log of 2, remember, is just a number, a value. If you want to write it as the approximation 0.693, to get a little better grasp on it. This side then would be taking the derivative of 0.693x. So the derivative of 0.693x is 0.693, or exactly our natural log of 2. So the right side of the equation, taking the derivative of x is just 1 times that constant natural log of 2. That side will be natural log of 2. Now, this side will be a little more involved, and this is where we need the implicit differentiation. We're taking the derivative of the natural log of y, but with respect to x. Well, the derivative of the natural log of y, we need to think of chain rule. Derivative of the outside, derivative of natural log is going to be what? Okay, derivative of the outside would be 1 over the inside. Or as Professor Berger says, the blop. Okay, 1 over the blop. Okay. And then we take the derivative of the inside. So, derivative of y with respect to x, dy by dx, or y primed. We don't know what that represents. All we can say is we're going to take the derivative of y with respect to x. It's not derivative of x with respect to x, but derivative of y with respect to x. Now, what are we actually trying to find? Well, we said we want to find the derivative of this function here. Well, that's saying in this notation, what is the derivative of y? What is y primed? So we need to solve this equation for y primed, and that's going to be our answer. Well, how do we solve for y primed? We need to get this part to the other side. So if we multiply both sides by y, we end up with this. Well, what was y? From the very beginning we said if y is going to be 2 to the x, so we can say y primed equals y times the natural log of 2. So that is where this natural log of 2 comes from. And a little bit different approach, still valid, but one thing we have to keep in mind, we must know one fact about either the exponential or the logarithm functions to be able to show the others. Okay. And we started with knowing the derivative of natural log of x is 1 over x. From that, using log properties, exponential properties, and the implicit differentiation, we're able to show what we've been working with, but this is why we have that natural log of 2 times the 2 to the x for the derivative. Questions?